All right, we're going to talk about some tricks to remember when doing constant acceleration problems. And hopefully you can come back to this later, as we go further down the road and you forget kind of how to do some of these, it'll be good to come back and use this video as a reminder. So typically when I'm talking about constant acceleration problems, it's not always the case, but in the instances I'm going to give here in the video, we're going to have the idea of when we're dropping something or we're tossing a ball up in the air, and therefore gravity is what is causing the acceleration, and that's a constant acceleration of -10 meters per second squared. So just a reminder of some assumptions, and I'm just going to list them here, and I might draw a motion diagram and talk about some things. So when you drop a ball, right, the initial velocity is 0 meters per second, right? Now, another assumption that we can make is if we're tossing a ball in the air. So the rest of these assumptions are going to be for that. So we toss the ball up into the air. It gets, oh, that's a horrible motion diagram. Sorry. Here, I'll put another little one here. And it comes down towards the ground. So at the very peak, at the top, the velocity at the top here for a moment in time is 0 meters per second. Now, if you're splitting the problem in half and you're treating it like this is the beginning and this is the end, then your initial velocity would be 0. But if we were doing it the other way and we were talking about the toss being the beginning and this being the end, then the final velocity would be 0. And again, it's just how you define your problem, right? Now, another thing to note about velocity is that the velocity, we'll call this initial up, and the velocity down are equal in magnitude but opposite in direction. So velocity initial is equal to velocity final, except they are, one is positive and one is negative, except the direction. So if I throw a ball up in the air at 30 meters per second, that means when it flies up to the top, it will stop, and then it will accelerate back down towards the ground, and if the ground is at the same relative height, then it will strike the ground at -30 meters per second. Now, it's common that people think, well, once something hits the ground, it stops, and that would be the final velocity then would be 0, but that's an incorrect assumption. When I say final velocity, that's the velocity right before the ball strikes the ground. Now let's talk a little bit about time. So when we throw something up in the air, the time it takes to get to the top is going to be equivalent to the time it takes to get to the bottom. So time up is here, and time down is here, and those two are going to be equal to one another. So if we can solve for time up or time down separately, then we know that total time is equal to twice time up, or it could be also equal to twice time down, just depending on how we set up the parameters of the problem. Now, given the fact that gravity is 10, roughly, it makes it really easy for us, if we're told a ball is thrown up in the air at 30 meters per second, to figure out the total time. And I'll derive that out for you, and then we'll talk about how you can do that without really thinking, right? So we want to know time. We have initial velocity is 30. We have final velocity is 0. So we know that final velocity minus initial velocity all over t equals a. And if I solve this equation for time, then I actually get that my change in my velocity, so v final minus v initial, all over acceleration is equal to t. Well, remember that I said up here you're going to have your final velocity. If we're talking about the part where we're throwing it up, your final velocity would be equal to 0 in that case, and it would cancel out. And so all you have is your initial velocity divided by 10, and they're both negative. Well, you would be in the -30 meters per second divided by -10 meters per second squared. And so I know immediately that if I take -30 and divide it by -10, I get 3 seconds. So If I toss a ball up in the air at 30 meters per second, it takes 3 seconds for it to come up to the top. And because up and down are equal, that means time total would be 6 seconds, would be my total time. Right? So let's say I toss the ball up at 50 meters per second. Well, very quickly, without doing any of this math, I know 5 seconds up, 5 seconds to come back down. That ball is in the air for 10 seconds. If it's going to be up in the air for 40 seconds, or if it's tossed up in the air and it's up in the air for 8 seconds, then I know that would be 4 seconds up and 4 seconds down, and the initial velocity would be 40 meters per second, and the final velocity when it strikes the ground would be negative 40 meters per second. So just a little trick in order to remember time and to solve for time there. Now, just one more quick thing when we're talking about setting, if we are treating something like a dropping problem, I want to show you another equation that you'll use pretty frequently. So we have the equation that d final, or the change in d, or the displacement, is equal to v initial t plus 1/2 at squared. All right? So this should be one of your constant acceleration equations that you know. Now, if we're dealing with a dropping problem, we just said that when you drop something up here at the top, the initial velocity is equal to 0 meters per second. So quite frequently when you're dealing with a problem where something is dropping or that initial velocity is 0, we'll often be referring to this equation. So t equals 1/2 at squared, where this term has canceled out. But again, that can only be used in an instance where the initial velocity is 0 meters per second. Okay. So again, this is all stuff we've talked about and that you've probably used in either labs or in some problems. But again, just a few tricks when it comes to constant acceleration problems to save you a little time.